Today, during my talk, I will give you a story about what happens to atoms when they get very, very cold. What I mean by very, very cold is basically the coldest place in the entire universe. And then I will tell you like when and how from there we enter the quantum world. So first of all, let's ask a simple question of what is basically ultra cold and what do we mean, how cold is ultra cold? So if you look at this basically like very everyday life sort of temperature thermometer, which is like we know the regular temperature is like from 100 C that when water boils, and then like normal human body temperature, or at zero temperature when water freezes. But if you look at like from this linear scale, if you go to zoom out and go to this logarithmic scale, you will see from this almost 0 Kelvin, which is the absolute zero, all the way to much, much higher temperature, we have this like a broad range of temperatures that exist inside the universe. So if you like focus on this logarithmic scale, so I want to tell you about like basically at each temperature, what is the speed of atoms like when they are moving in that sort of temperature. So let's just start from the one of this hottest place, which is the center of the sun. We know temperature is about like 10 million Kelvin, and like the speed of atoms moving around that is about basically the speed of like rocket launching. So it's about 30,000 miles per hour. And if you go to the other side of the spectrum, like you can look at this, for instance, the temperature of this lecture hall, and what's the speed of atoms moving around here, and then go through the coldest part of this spectrum. The coldest place that we know, I mean, if you exclude our experimental lab, is outer space, which the temperature is minus 270 Celsius. It corresponds to basically 2.4 Kelvin. And the speed of atoms there is basically 30 miles per hour, is like moving a small car. But what we can do in our lab is that we can cool atoms down like about 6 to 9 orders of magnitude cooler than outer space. So literally we are in the coldest place in the universe, with like atoms moving around 3 meters per hour as fast as a snail can move. So we want to see basically what happens to atoms when they get that cold. To answer this question is we want to meet this very famous, one of the biggest key figures in history of quantum mechanics, Louis de Broglie, that basically proposed a great idea that for any atom with momentum p, you can like consider a wave. In other words, like atoms, particles are also waves. And he basically corresponds a wavelengths to each atoms with this elegant relationship that we have like these wavelengths lambda, which corresponds to like is proportional to 1 over p with this like tiny value Planck's constant that we can see is like 6 times 10 to the minus 34. So let's just bring 2 examples. The first example would be a baseball. Basically, with assume that it's moving with 40 meters per second and with like a mass of 0.1 kilogram. And if you calculate this relation, basically this wavelength, I lost my pointer here, you can see it's like 10 to the minus 34 meters. So it's very tiny. It's too tiny to be observable. So we can't see any wave nature of a baseball, right? So this is like classical realm. But if we go on the other side, let's assume we have an electron instead that is moving exactly with the same speed, 40 meters per second. But if you calculate the same wavelengths, you get to a very different number. Is 2 nanometers. If you all remember, nano is 10 to the minus 9, right? So it was like from 10 to the minus 34 to 10 to the minus 9. Now we begin to see these quantum effects. This is where basically the size of the electron, the size of the particles is now much smaller than these wavelengths. So here is when these quantum effects start to basically unfold. So then I would say, okay, let's assume we have not just one particle, we have like a bunch of atoms in a gas moving around, and I start cooling them down. So I talked about like cooling versus velocity, right? Like Now assume that I'm cooling them down so they get slower and slower, then that momentum gets basically smaller and smaller, right? So what happens if you get to like cool them down further, you see that this wave nature of each particle start to show up. And if I go even further, like if I cool down even further, I see this like waves of this particle start to overlap. But then we have a question of like, okay, what would happen if these waves start to overlap? To answer this question is basically it all depends on the particle's personality. So if you want to know what happens to these particles bouncing around each other, we should know what are those particles. So in quantum mechanics, all particles falls into two categories. Like these two categories are basically the fundamental class of particles that like for each class determines the rules, the statistics, and all physics that govern into their system. The first category are fermions, and the second are bosons. So let's just see what are they. For fermions, basically they are very antisocial particles. They don't want to behave the same, so they're very trying not to actually act in the same and not occupy the same state. These particles have half integer spin, basically like 1/2, 3/2, 5/2. And the most famous example of there are most basically elementary particles like electrons, protons, and neutrons. And if you look at these electrons, remember in high school probably you just like learn about this Pauli exclusion principle, which says no two electrons or fermions can occupy the same quantum state, right? So basically this is the reason that we have this shell structure or in the atoms. You have this like the reason that chemistry works, the reason that we can form molecules, and also the whole idea of this periodic table is coming all from this like filling the shells or orbitals around the nucleus, right? And so if we cool them down, what would happen is that because they cannot occupy the same quantum number, what would happen that they start from the very like lowest energy and they start stacking up one by one all the way to the Fermi energy, which is the highest field level in energy. And they cannot basically, even if you have a temperature of 0, even at absolute 0, you have a significant amount of energy, which we call it Fermi energy, or pressure, which is famous for like so-called Fermi pressure. So they can't actually, in any sort of low temperature, they cannot occupy the same state. But how about bosons? They're exactly completely different. They have different personalities. They are genuinely sociable, and they want to actually act exactly like each other. So they have the bosons have a spin like integer spin, like 0, 1, 2, and they are not subject to Pauli exclusion principle, which means they can actually occupy the same quantum state, and they want to. They prefer to actually, as you cool down, they prefer to occupy the the lowest energy state of the system. So the significant consequence of this phenomena is that this is how laser works. Why? Because photons are actually bosons. So when when you're inside the laser can force photons to actually emit coherently. And the reason that you see this laser pointer is directional, intense, and coherent is because we have photons that are occupying the same quantum state. Okay, so let's see what happens if we cool down bosons. We said they start basically overlapping, right? And they want to occupy the same quantum state. So if we start again, we have a bunch of gas, we start cooling them down, their wave nature of these particles start to overlap until something fascinating starts to happen, which you see suddenly all of these particles start to form a single coherent wave, which is quite fascinating. The more real picture of it is that, so exactly like what happens inside the water, if you start cooling down the water, suddenly you get the phase transition from a liquid to something like solid, right? You go exactly from at 0 temperature, you get from liquid to ice. And this is sort of the same, not the same phase transition, completely different nature, but this is another phase transition. And people used to say this is the fifth state of matter, basically. So we know this gas, liquid, and solid, and then we realize we have plasma, and this Bose-Einstein condensate, which is basically this matter wave is the fifth nature, the fifth state of matter. So as we cool down the particles, we get to this gigantic microscopic wave that we can see even by eyes. So the idea of this Bose-Einstein condensate, as it's obvious from the name, is coming from theoretically from Bose and Einstein. And these two people basically predicted completely with theoretical calculation in 1924 and 1925. And so they realized this is completely new state of matter. So there is no, basically, it's not just very cold gas. It's like suddenly a new phase. And so they didn't know how to cool atoms to prove this experimentally. 70 years later, these three people, Wolfgang Ketterle, Eric Cornell, and Carl Weinman, they actually started to like discovering the same phenomena. These are real pictures. They actually saw this amazing phenomenon with two atoms, rubidium and sodium. So as you see, as we are like above this critical temperature, which where the phase transition happens, we have this cloud of atoms that start to occupy, sort of overlap these waves. And as you go below and below, further below than the critical temperature, there's a spike. That this spike basically is a real matter wave. So, and these three people actually got this Nobel Prize in 2001 for this like amazing work. Okay, so we end up from this like classical cloud of gas to an entire quantum wave matter. But how can we prove that these are actually waves? So one way to do that, if you remember it from this like Young's double slit experiment, if you have a planar wave, a coherent planar wave, you pass it through two slits, you produce two basically circular waves, and they start to overlap, right? So one way to see you have waves is that to see them, they produce these fringes, this interference, right? We know that waves interfere, and we have these like constructive and destructive dark spots in this screen. So one way to do that is if I have two BEC, two Bose-Einstein condensate, and let them overlap, I should see something similar. So this is basically what I would expect. And in 1997, 2 years after they discovered it experimentally, they started having it a BEC, and they made it in two different BEC, and they turned off the trap and they let them to overlap. And once they did that, these four people realized that this is actually what they saw in the screen, which is a crazy phenomenon. So you see that this is actually this like interference pattern or fringes, bright and dark spots, exactly like you have two waves. But they're actually atoms with masses, with electrons, protons, and neutrons, which is quite fascinating. And if you see that, like basically, scale is 1 millimeter, which means this is like obvious with naked eyes. So after this, like all of this fascinating phenomena, people like started. If you heard about this BEC or Bose-Einstein condensate, people calling it laser, atom laser, is basically because of that. Because like you see in laser, you have massless photons doing the same, but here we have actually laser of atoms. It's one of these the most famous pictures in atomic physics. But this is not the end. Actually, from here, it's an opening door to like all of these quantum discoveries and like quantum texts that we have. So from here, after you have a BEC, another phase that you can basically explore is superfluidity, which is when under some basically conditions, your Bose-Einstein condensates start to flow without any friction or without any viscosity. And also, if you can produce, like I cannot go through fermionic part of this phenomenon, but like if you can produce Fermi superfluid, that's the direct connection to understanding how superconductors work. The other sort of application of this of ultra cold atoms is that you can put these like ultra cold atoms into optical lattices, and then like you can explore so many of these complicated, complex quantum materials that are not easy to understand with even supercomputers. The other application of this sort of field is atomic clocks, that we know is the most precise clocks in the world. And this is how, this is where we use, basically in GPS, we're using atomic clocks. And also you can explore so many of these fundamental physics with high precision measurement. And okay, what I was saying is all happening in our lab. Here is inside our lab. You see, we work with laser, with basically magnetic coil, with coils that produce magnetic field. We work with vacuum chamber, and all together we produce these. As you see, this shiny ball is coming and going. There are actually trapped lithium inside our chamber. And if you're interested, that would be great if you can see our website as well. And we can start from trapping atoms here and just explore all of these quantum techs and other applications with ultra cold atoms. All right, by that, I want to tell you, shift basically to the beginning. I said, okay, we start from cooling atoms lower and lower until we get to a temperature that the quantum worlds start to unfold, right? But I didn't mention how we get there and what are the technologies or techniques that I use to get to that ultra cold temperature. And that is the answer of this question is the subject of the next talk. And by that, I will end my talk, and I will be happy to take questions. Thank you.
Thank you so much. We have time for one question as we get the next speaker set up.
Sorry.
Yeah. Sorry, Len, passing that over. Thank you. So you mentioned that the Bose-Einstein condensates form when you supercool the bosons, right? And so they form individual waves at first, and then they superimpose to form a bigger wave.
Mhm.
Could it also interfere destructively instead of constructively?
So again, because there are you see these waves, all of them are going to overlap because of this fundamental nature of bosons. They want to energetically is more favorable to occupy the same states. So they want actually to overlap to each other, and this is how they lower the energy of the system.